Hi there, physics students. In this video, we're going to be discussing some common wave characteristics. You've already been introduced to these topics in the reading and in previous assignments, but what we're going to do here is to quantitatively analyze this wave. Well, what does that mean? We're going to do some math to understand the wavelength, the period, the frequency, and speed of this particular waveform based on the measurements that have been given. Now, before we start our analysis, it's really important that we have a common vocabulary. So what we have here is a wave diagram that has some labels or some arrows pointing to certain parts of the wave or certain features of the wave that we should identify so that we can have a clear understanding of what's happening. Now, in a moment, what I'm going to ask you to do is pause the video so that you can fill in the blanks to the best of your knowledge based on your previous assignments. And then we'll go ahead and restart the video when you're ready and see how well you did. So go ahead and pause the video. Okay, how do you think you did? Let's see. Well, first of all, I think it's really easy to see that this is a particular type of wave, and there were two types of waves that were discussed in the chapter. This is the type that has oscillations that are moving up and down, or vertically in this case, while the wave travels across the page from left to right, or horizontally in this case. Because these two motions, the motion of the wave and the motion of the oscillations, because those are perpendicular, we often refer to this as a transverse wave. Now, a transverse wave just means that the oscillations are perpendicular to the motion of the wave itself, or the traveling wave itself. To understand a little more about what these components are, let's see how you did. So first of all, the clear parts of the wave that we might describe are, the ups and downs, if you will, so the high points and the low points. The high points we often refer to as crests, and the low points we refer to as troughs, like the crest of a hill and the trough into which you pour something. So these two components of the wave have to do with the maximum displacement in the upward direction and the maximum displacement in the downward direction. Well, what is that maximum displacement, or what is that? So in other words, what I'm talking about here is what's this called here when it goes up to the maximum and it goes down to the minimum, or the maximum displacement in the negative direction. Again, this might be the positive direction and this might be the negative direction. Okay, well, those displacements, or the height of this crest and the depth of this trough, are both referred to as the amplitude. Now, the amplitude in an ocean wave might be the height of the wave. It might be the volume of a sound wave, and it might be the brightness of a light wave. So the amplitude is how much this wave is displaced from equilibrium. Well, that sort of gave us a third answer, which is, of course, the equilibrium position. And this equilibrium position is this dotted line here. We might call this the equilibrium. And you know what equilibrium means. It's where the wave, or where the string or the spring or the rope, or even the water, if these were water waves, that would be the water level when there was no wave present. So that's the rest position, if you will. And so the amplitude, well, I misspelled amplitude, didn't I? So the amplitude is really the displacement from this equilibrium position. So the crest is a positive displacement of the waveform, or the water, or the rope, and the trough is a negative displacement where equilibrium is the midpoint. Now, the last component that we see here has to do with a measurement from 2 points on the wave. For example, crest to crest. So if we look at this from this portion of the wave all the way down to this portion of the wave, okay? And this measurement shows from the equilibrium point, where the wave is crossing up on the equilibrium point, to where the wave is crossing up on the equilibrium point here. Now, that's, if we look carefully, and you take the path that this wave is traveling, and you look, it goes through all the way up and then all the way down, and then it comes back home to equilibrium. So in other words, it goes up, it goes down, and it comes back home to equilibrium. That is the length of one cycle before it repeats itself. We refer to that as the wavelength. And as you might imagine, it's the length of one wave. And so is this the wavelength as well? Well, let's see. So we start at a crest at the top. We go down all the way to a trough, and we come back up, and we come back up to the same crest again and ready to go down again. So that means that is also the wavelength. Now, some people like to say that the wavelength is the length of the wave. Some people like to say that it's the distance that a wave travels through one oscillation or through one cycle. Either of those are fine. So hopefully you got some of these correct. And now we can move on to taking a look at that other waveform that we had. So I think you can see that this is, of course, a transverse wave, as we mentioned before. It certainly has wavelength that we could define. It certainly has a period. Now, period is an interesting one we'll talk about in a minute. It has frequency and it has speed. Well, let's see what these terms actually mean. Now, we've already described wavelength, and I think I used the pink pen to describe the wavelength. So let's go ahead and use that again. And the wavelength really is, well, gee, that's just the length of one cycle. Now, I said cycle instead of wave. I could have put wave here, and I'll just put it in parentheses. But really, it's the length of one cycle, because remember, this is an oscillation. This is something that's moving back and forth, up and down in this case, as the wave travels. So it's the length of one cycle, and we can point out that cycle very simply. If we started at 0, it would be one cycle here. It could be, as we saw in the last dimensional diagram, it could be from a crest to a crest. It could be from a trough to a trough. Or it could be from anywhere on one wave, let's say, oh, I don't know, right here, up and down to the next point on that wave. All of those are one wavelength, because you can see all of these dotted pink lines that I'm making here are all the same length. They're all the same distance. Now, let's analyze this particular waveform in order to understand what the wavelength actually is. So what is length? Well, the length of something we typically measure in meters. So it's the meters, okay, the number of meters for one cycle, the length of one cycle. So I'm going to say the meters per cycle, and I'm just going to abbreviate that CYC. So it's the number of meters over the number of cycles. That would be meters per cycle. Now, when we look at this waveform, we see a measurement that says 18 meters, but notice that 18 meters is not one cycle, it's many cycles. So whenever we do a wave analysis, one of the things I like to do first is to simply label or count the number of cycles that are dimensioned. So in this case, I'm going to start at 0, because just like a number line, you start at 0 where it's first dimensioned, and I'm going to count 1, 2, 3, and 4. So I see that we have 4 cycles measured at 18 meters. Well, what does that mean? Well, let's see. Meters per cycle. So we're going to say the meters is 18 meters divided by how many? 1, 2, 3, 4. 4 cycles. And that's going to give us a numerical value of 4.5 meters per cycle. Now, therefore, we can report that the wavelength, which is given the symbol lambda, a Greek letter lambda, and that lambda just means the wavelength, or refers to the wavelength, is 4.5 meters. Now, I thought it was meters per cycle. Why didn't I put meters per cycle? So it's just meters because the wavelength, as we said, is defined as the length of one cycle. So we don't need to put meters per cycle, we can just put meters. Let's go ahead and put a box around that one so we understand what we have here. The wavelength is 4.5 meters. And I think if you divide 18 by 4, you'll get 4.5 every time. Now, The period. Now, you may remember from the time when we discussed planetary motion and circular motion that the period is the time for one cycle. Okay, so the period is the time, and I'll put this in parentheses too, because sometimes people describe period in different ways, but we'll call it the time for one cycle. Now, I could have said wave, but let's call it a cycle, but I'll put wave in the parentheses here. And we know that it's one cycle takes place in a certain amount of time. So it's the time. And what do we like to measure time in? Well, we like to measure time in seconds. And that's seconds for one cycle. So per cycle. So it's really the number of seconds over the number of cycles. Now, if we take a look at our wave, oh, here we have a time that's measured, 2.5 seconds. Now up here we had 4 cycles dimensioned, but now here down here we have more than 4, clearly because this dimension is longer than the other. So let's go ahead and label those cycles. Again, we'll start our number line at 0. 1, 2, 3, 4, 5 cycles. Now we have 5 cycles labeled, so we know that 2.5 seconds is the time to do 5 cycles. Now I'm pretty sure you can see where we're going with this. So if we plug in 2.5 seconds over 5 cycles, I'm going to end up with a measurement of period. The time for one cycle is going to be 0.5 seconds per cycle. So we can report now that T, capital T, because it's a special time, is equal to 0.5 seconds. Now, why didn't I say seconds per cycle? Because that's what it said over here. It said seconds per cycle. I didn't say seconds per cycle because I don't have to, because the period is the time for one and exactly one cycle. So we have a wave that has a lambda or wavelength of 4.5 and a t or the period of 0.5 seconds. Now let's talk about frequency. Okay. Now what does frequency mean? If something is frequently happening, that means it happens often. Okay. If something is not frequent, it happens less often. So the frequency is really how, and I'm going to put that in parentheses too, because we can define it in different ways, but this is the easiest way, I think. How often a cycle repeats. So if it happens really frequently, then it happens very often. If it happens less often, it happens with a lower frequency. So usually we say how often it repeats, per time. Now I'm going to put that in parentheses because, again, just want to make sure you analyze the wave as it's said here. So what does this mean? It says how often a cycle repeats per time. So that's a cycle in a certain amount of time. So that's like the number of cycles over the number of seconds. Now, if we count the cycles in the number of seconds, well, first of all, let's fill in the number of seconds because we know that it's 2.5 seconds because we know that says seconds. This is the number of seconds, and we already counted the number of cycles as 5 seconds. Okay, and I'm sorry, cycles, pardon me. And when we divide 5 by 2.5, you'll see we get 2.0 cycles per second. Now, interestingly, if you look carefully before we give you this final answer, take a look at this. Notice that period is seconds over cycle and frequency is cycles per second. So let's take a look. If we say 2.0 cycles per second, that means that we can report the frequency as 2.0 hertz. What hertz? What is that? Well, hertz is just a unit, okay? This is a unit called Hertz, H-E-R-T-Z, named for Heinrich Hertz, who did a lot of work with analyzing cycles and waves and so forth. So we have our frequency at 2.0 hertz. Now, notice, if you will, that period is cycles per second and frequency is seconds per cycle. No, I said that backwards. Period is seconds per cycle, and frequency is cycles per second. So you can see that these are just the inverse of each other, and that's going to be really important to remember. So let's just go ahead and make a note of that. That means that period, okay, t is equal to 1 over f, and that frequency is equal to 1 over t. So they're the inverse. And I think you can see that because, again, period is seconds over cycle, frequency is cycles over second. So that's just inverting those two. So let's talk about speed. Well, what is speed? Well, duh. Speed is just kidding here. Speed is the speed of the wave, or the wave speed. Now, speed, we know, well, we know what speed says. We know what speed is. I mean, we know that speed, very simply, is distance over time. So x over t. Okay, that's cool. But with a wave, what's the distance? What's a distance that we might want to use to measure our wave distance for speed? Well, I think a distance that we might want to use is the wave length, the lambda. Okay? And when we want to talk about the time, we don't want to talk about just any time. We want to talk about the time for a wave. And the time for a wave is the period of the wave. So we're going to go lambda over t. So that means v, certainly it's x over t, distance over time, but the distance we want to talk about is the wavelength, and the time is the period. So let's go ahead and fill that in, okay? And we can say the wavelength, well, that was 4.5 meters per cycle. What? I thought it was just meters. Well, just bear with me. I'm going to use the 4.5 meters per cycle because I want to show you how the units cancel. And the period, of course, is 0.5 seconds per cycle. And I think we can see that 4.5 over 0.5 is 9.0. What are our units? Well, if we look carefully, we can see that we have meters in the top, seconds in the top, cycles. So cycles cancel, okay? And we end up with a unit of meters over seconds. And that checks out because that's the unit of speed. Now, interestingly enough, the way we got this was we said v is equal to lambda over t. Well, if we just write this down over here, if we say v is equal to lambda over t, well, that's the same as multiplying lambda, the wavelength, right, times over 1 times 1 over t. But wait, 1 over t, take a look, 1 over t is f. So we can also say that this is v equals lambda times f, because of course 1 over t is f. The reason I say that is because this is the wave equation comes in two forms. You might see it as v equals lambda times f, or f times lambda, or you might see it as v equals lambda over t, which are the same thing. So let's go ahead and calculate that one as well. And I think we can use orange down here because we haven't used that color yet. And so we can say v is equal to lambda times f. And when we plug and chug there, we can say the lambda, of course, is, that's the same thing as we had before. Let's go 4.5 meters per cycle. Now, I know I'm using meters per cycle because I want to make sure you guys understand what's happening. And it's going to be 2.0. Now, instead of using the hertz, which it's hard to see the cycles in there, I'm going to use the cycles per second. So I'm going to go cycles per second. And lo and behold, we get 9.0, because that's 2 times 4.5, and that is going to be, what are our units going to be? Oh, I see. Look, the cycles cancel again, and we get meters per second. So notice that we got the same answer for the wave speed when we did it lambda over t as we did for lambda times f. Now, that's pretty much it in terms of analyzing a waveform. Hopefully you got something out of this. If you have questions, please refer back to this film or check your handouts and make sure you have all the tools that you need to analyze the wave. Thanks for watching.